In the last two lectures, we have been setting up MetaMask wallet. In this lecture, we'll continue with AI lecture, and I will be talking about the signing of messages. So you are free to skip if you already know how the transaction is signed. Okay, so we can start, and by the way, you can close this MetaMask and you can open it normally as an extension. So you can close this. Okay, this resource you already have. And in a Brave browser, you can simply on the right side in the extension tab, you have extension, you can pin MetaMask and you can open it as this. And here are your networks and the accounts. Okay, but now to the point. I will go to my drawing tool and I will be drawing the transaction. So Carbo here. I don't know if it is enough for me, the space. Okay, I'll open here new space. Okay, so we have basic understanding how the transactions are created, right? And what data transaction contain. So when we are sending transaction to Ethereum network, okay, I can draw here. So when we are sending transaction to an Ethereum network, transaction looks something like this. So transaction contains a field from. That's the address from which the transaction is going, 7 to so on, to address, okay, the 0x31 AB and so on. Okay, 20 bytes, both of these addresses. Then we are sending also value in way. So this can be, I don't know, lots of way. Okay, value, gas limit. So in how much gas we are willing to pay for a transaction. In a normal transaction on Ethereum, it's 21,000 basically. And then nonce. Now, nonce is the number of the transaction which we are sending. And all this basic data contains the base transaction, right? That's the base transaction we are sending to Ethereum network. That's a base transaction. So we want to send this transaction to Ethereum network, right? So we want to send it to Ethereum network so it can be processed by the nodes and it can be added into block. So we can transact the data. We can transact the Ether. But what if there are some listeners on Ethereum network, and what they will do? They want to replay the transaction. Basically, the order of the transaction is not guaranteed, right? So what is stopping the hacker or some person just to take the transaction and create a copy of the transaction and simply replay it to the network and change some data, right? So change here, for example, the value. Okay, either increase value, so it will drain our wallet from the Ether and so on. So what is stopping this replay attack? The first thing, what is stopping it is the nonce, what we are providing here. Since there is a transaction with this nonce in the network, the same transaction with the nonce cannot be added, all right? Because this nonce has to be resolved, and the next nonce in the order has to be nonce 3. Okay, so the next transaction, what should go to the network should have a nonce 3. So that's the uniqueness of the transaction is the nonce also. Okay, so with this keeping the track of how many transactions we send. So when we create a transaction, this one, for example, somebody else can just copy the transaction and send it as a transaction too. Okay, but the hacker can do simple thing. He can change the nonce. He can copy the transaction and he can change the nonce to B3, for example. Okay, so here nonce 3, all right, and nonce 3, and simply the hacker will change the value and it will basically change some data. So it will mess up with our account. Okay, that's not so simple, because in order to copy our transaction, the hacker would have to sign the same transaction. Okay, and the hacker doesn't have our private key, because private key, as I told you in the last lecture, private key we are keeping locally on our computers. Okay, so private key is some secret information, this 32-byte number that only we have it, and with the private key we are assigning the transaction. Okay, so what basically going to the network is not just the raw transaction as this, but it's a signed transaction. So what we are sending here is the signed transaction. And we are signing this transaction with our private key. Okay, so if hacker would want to basically send the transaction, he would change the data around, and he would change, for example, nonce and so on, and he would try to sign a transaction, but the transaction simply would be signed with the wrong data, and then it couldn't be decoded, because you can verify the transaction only with the public key. Okay, so that's a private key, right? Private key, and also we have a public key. Okay, I should make it as a secret key, because the public key also is a PNK. So yeah, we have a private key and a public key. Public key. Okay, so on the base level, it can work like this. In the background, when we are sending a transaction, we are assigning it. So it's going to some function sign, when it will take the message, right? It will take the message, and also our private key. I will mark it as a private key, as a secret key in this case, because public key has the same credentials, so secret key I will call it. Okay, and this will create a signature. So this here, I don't have much space, guys. I don't have where to write. So this will create basically this will resolve into signature. Signature. This will create a signature. Okay, signing message, which messages are a transaction with the secret key, with the private key, will create a signature. So every node on the network that confirming the transactions, they want to add them to the blockchain, they has to verify these transactions, and they will verify them with their public key, because public key is public for our account. Okay, so anybody can retrieve the public key from our account. So basically, node will check for it, and they will run their own function. The nodes will run function verify. All right, and they will verify our message. Okay, so this will be message, that will be a transaction, basically about transaction data, so message. All right, they will provide us our signature of the transaction, SIG, I will call it as a SIG, message, SIG, and also they will provide our public key. Here I will mark a public key, PK for a public key. And this will resolve into a true or false value. Okay, true or false. Okay, so one more time. Before this transaction will get into the network, it's signed. Okay, it's signed with our private key. Okay, it's going to some sign function. We'll take our transaction message. All right, together with our private key, it will generate a signature. This signature, therefore, will be part of the transaction. Okay, it will be part of the transaction. The miners on Ethereum network that are processing a transaction has to verify the transaction if it's really coming from the user that's sending the transaction. So they are running their own function, verify, and they will run this function on the message, so on the transaction data. The signature is a part of the transaction, and also public key. Public key they can also generate from a transaction, and this will return them true or false. Okay, so if the hacker would try to replay the attack, he had to create a signature, and of course, when the nodes would verify this with the hacker public key, it would return basically false. So it's not so simple. Okay, so only us, the holders of a private key, we can send the transactions, and we can also prove that we are the senders. That's why the private key is very important to keep secret. You should never ever share it with somebody, even when somebody pretends that it's from Ethereum development team or somebody's asking you for this. Never. Always be very suspicious when somebody asking you for very personal data on the Ethereum or on any network. Okay, so that was just the base level. I can also go a little bit deeper in this. What's actually happening here, when you're creating signature of this, you're running something like this. These data are first encoded into the bytes in hexadecimal format, but the signature function looks something like this. It will return you three parts, RSV parts, as they are parts of the signature. You don't need to know much about them. I want to talk about them later. RSV part, and the signature looks like this. The signature function basically take the hashed version of your transaction. So it will take the KETSAC 256, and your RLP encoded transaction, and provide your secret key Okay, so basically that's how the signature is generated. it's the hashed version of your RLP transaction plus your secret key, your private key. This will generate these 3 parts, RSV, and these 3 parts are also part of the transaction. Okay, so every message, every transaction message is signed before it's emitted to the network. We can take a look on a few resources I have prepared for you. I will include them in the description. First thing here, you can see here that there is example of transaction message from to gas limit, nonce value. Also, there are some extra fields. I think fields there, they have been added, I guess, in the new Ethereum update. I didn't see them before, so they are part of this, I think, of the new update. But basically, what's happening, you're running them through a account signature transaction. So you're basically signing it, and this you are signing your transaction, and this will basically, as you can see here, when you're signing a transaction, you are transforming some fields. So for example, gas is in hexadecimal format. All of these things are in hexadecimal format. Nonce is in hexadecimal format, and this will be this will create this raw transaction. This is basically RLP encoded transaction. I'll be talking about this, and here is in a JSON format. This will generate these 3 parts, RSV, and thanks to them, they can verify your transaction that you're really the sender. If you provided correct private key, they have your public key, so they can verify the transaction without knowing your private key. All right, so that's on the base level. We can take a look on actual transaction. Here in ADB Toolkit, remember I include this resource in the lecture. We can decode transactions. So here is example transaction, just sending Ether from account to account. We can check here, get raw transaction hash, and this raw transaction hash that's emitted to the network. This transaction hash already contain the part of the signature, this RSV part. So when I will go here, I'll copy this, and I will go to Toolkit, and I will decode this transaction. You will see this is decoded transaction data. So, and here is the signature part. So here, for example, this R part of the signature, you can see it's a part here. This here of the raw transaction data, and here S. Okay, this is a part of here, this transaction data, and yeah. So from here, should we be able to find the from? From, actually, I think from it's okay, or it's in some different format, so it's not part. I didn't see it there. Okay, for example, the Ether, the amount of the gas limit, so gas limit 21,000, it's also part of your transaction, and so on. So this is basically RLP encoding. So when I look for a 21,000 in hexadecimal format, for example, okay, so hexa decimal to decimal. All right. I should be able to find also this is part of this raw transaction data. Actually, decimal to hexadecimal. Okay, convert, and this should be also part. You can see all these data are encoded here, basically in this raw transaction hex, and that's what they emitted to the network. And thanks to this, they can verify that you are the sender of the transaction, that you provided it correct. So that prevents the hacker to just simply replay your transaction. Okay. All right, guys. So yeah, every transaction has a nonce, as I told you. That's basically keeping a track of your transaction. It creates also some uniqueness to transactions, so transactions cannot be replayed before the transaction is sent. This is encoded. Your transaction is encoded and also signed through the sign function. The signing Kesak RLP transaction data with the private key. This will generate these 3 parts. These 3 parts will be part of your raw transaction data. All right, and then the backwards, the nodes in the network can verify. They take your message you have generated with the signature. You have generated these RSV parts, and they will take public key, and they can say true or false. Okay, guys, that's gonna be. If you have any questions, I know this topic is a little bit maybe hard to understand. I want to go through this also in the future lectures. We will leave it here. I would like to focus now on coding of our application, so we can finally create some front end here. All right, guys, so that's gonna be it, and I hope to see you in the next one. Cheers.